this example shows you how to use boundary conditions and solve for constants using those boundary conditions. This is a more complicated problem than perhaps you've seen before, but once you realize what the boundary conditions are and also you keep track of your math, you should be able to do a problem like this anytime. So we have two immiscible fluids, so they each have their own viscosity, and they're pumped through a pipe with a circular cross-section, and there is a pressure difference, and as I said, there are two different viscosities. One viscosity, mu1, with that fluid forms an inner core, and the one with mu2 forms an outer shell around the core. And we're assuming that the interface between them is at d/4. So a general solution for pipe flow with a radial velocity distribution has been obtained by using the Navier-Stokes equations, and we come out with U equals r squared over 4 mu dp dx plus c1 over mu ln of r plus c2. However, we have two different velocity profiles, so we'll call that u1, and u2 is going to be exactly the same, except our viscosities are different, and our constants will be different as well. So we're going to need 4 boundary conditions because we have 4 constants, and let's draw a picture. There's the inside, there's the outside, and the first boundary condition that we're going to look at is that at r equals 0, so the very center of the pipe, the velocity has to be finite. And if that's the case, the only way that can happen is if c1 equals 0, because ln of 0 is infinite. So the only way to make that, keep the velocity finite, is to get rid of that whole term altogether. We also have at r equals d/4, so that's the interface between the two. We know that u1 is going to equal u2, and we also know, so this is our third boundary condition, that the shear stresses are going to be equal. And our final boundary condition is based on the no-slip condition at r equals d/2, which is at the wall, or the pipe wall, our velocity equals 0. So we've already solved for C1, and there are a number of ways to go about this. Using any one of your boundary conditions, you can solve for your constants. In this particular case, using tau1 equals tau2 is probably the easiest boundary condition to work with. And the reason for that is since tau equals mu du dr, when we take a derivative of either one of our velocities, we're going to end up dropping out some of our constants. So let's do that here. All right, let's look at tau1. So tau1 is mu1, and then du1 dr is r over 2 mu1 dp dx. And notice that the mu1's drop out. So our tau1 equals r over 2 dp dx. Now let's look at our tau2. So that's mu2 du2 dr, which is r2 mu2 dp dx. But now we have to keep in that C3. We had gotten rid of C1 already. Mu2 over r. And again, we can rewrite this that tau2 equals r over 2 dp dx plus C3 over r. And if you take a look at them, if tau1 has to equal tau 2. That means r over 2, regardless of what the r is, dp dx has to equal r2 dp dx plus c3 over r. And the only way for that to happen is for that to be 0, so c3 equals 0. So now we've taken care of two of our constants. They're both 0, c1 and c3. So the next thing to do is to look at our boundary condition at r equals d over 2, u2 equals 0. So we can write our u2, d over 2 squared, that's our r squared, over 4 mu 2 dp dx plus c4 equals 0. That lets us solve for c4, which is minus d squared 16 mu 2 dp dx. So now we have 3 out of the 4. We've left, of course, the hardest for last. And this is at r equals d over 4, u1 equals u2. And we should always leave this one for last, just because when we have all the constants in it and we haven't solved for it, we're going to have equations with too many unknowns, and we're going to have more information in order to solve it. So here we are with our final boundary condition, and let's set them equal to each other. So this is at d, r equals d over 4. So that's d over 4 squared over 4 mu 1 dp dx plus c2, so that's the only constant we haven't solved for, equals d over 4 squared 4 mu 2 dp dx, now our constant, minus d squared over 16 mu 2 dp dx. So that lets us solve for c2, which is d squared over 64 dp dx. So I'm pulling that out of each one of the expressions. 1 over mu 2 minus 4 over mu 2 minus 1 over mu 1. And when we put this together, we get our d squared over 64 dp dx, and I took the minus sign out there, and we're left with 3 mu 1 plus mu 2 all over mu 1 times mu 2. So when we put all of our constants together that we solve for and put them back into our u1 and u2, we end up with the following equations. So our u1 is 1 over 4 mu 1 dp dx r squared minus d over 2 squared, and then here's our mu 2 plus 3 mu 1 over 4 mu 2. Our u2 is 1 over 4 mu 2 dp dx r squared minus d over 2 squared. And the difference in complexity between these two is because we had a boundary condition where u2 equaled 0 at the wall.